Hi, welcome to this short tutorial on statics of solid mechanics. In this short tutorial, I will take you through finding the weight W of a body on a surface and the weight WH at an elevation h above a surface. My name is Adam Gatogo. Thanks for joining me. Now the weight of a body is defined as the product of mass and acceleration due to gravity. Thus, W equals to mg, the mass times gravity. Now, weight is also force exerted by the earth on a body. That's W equals to F, that's the force. Weight equals force. Now, from the law of universal gravitation, the force exerted by the earth on a body of mass m is given by F equals to g, the universal gravitational constant, times the mass of the earth times the mass of the body all over the square of the radius of the earth. Now, if W equals to F, then we can equate these two equations. That's W equals to mg and then F equals to this expression. When you do that, you have mg equals to g times me times m all over re squared. Now, when you simplify further and your mathematics is correct, you will get G equals to the universal gravitational constant G times the mass of the earth me times all over the radius of the earth squared. Now, at an elevation h above the earth's surface, and by universal gravitational law, Fh, that's the force at that height, will be equals to the g times the mass of the earth times the mass of the body over the radius of the earth plus the elevation all squared. And to find the weight of a body at a height, you will have to multiply the mass of the body with the gravity at that height. So if WH equals to FH, then we can equate these two equations together, these two expressions together. MGH is equal to GMEM all over RE plus H all squared. So when you do that and then you simplify further and your mathematics is correct, you will get GH equals to G times ME all over RE plus H all squared. And then when you divide, this is our equation 2. When you divide it by our equation 1 here, you realize that GH equals to G times RE squared over RA plus H all squared, where G is the gravity at an elevation h above the Earth's surface and G is the gravity on Earth's surface. Now let's take a look at this question and solve it. When the Mars exploration rover was fully assembled, its mass was 190 kilograms. The acceleration due to gravity at the surface of Mars is 3.68 meters per second squared, and the radius of Mars is 3,490 kilometers. A. What is the rover's weight when it was at sea level on Earth? B. What is the rover's weight on the surface of Mars? The entry phase began when the spacecraft reached the Mars atmospheric entry interface point at 3,622 kilometers from the center of Mars. What was the rover's weight at that point? Now, in a question like this, what have we been given and what are we looking for? We've been given the mass of the rover to be MR equals to 190 kilograms, and then gravity at the surface of Mars, that's the planet Mars, equals to 3.68 meters per second squared, and then the radius of Mars also have been given us to be 3,490 kilometers, and then you convert it into meters because you are working in SI units, And then when you do that, you will get 3,490 times 10 exponent 3 meters to be the radius of the Mars. Now we are looking for the weight of the rover at sea level on Earth. But we know on Earth, gravity on Earth is 9.81 meters per second squared. So you carefully slot in the values of the mass of the rover and then the gravity on the surface of the Earth. And when you do that, you will get WR, which is the weight of the rover, to be equal to 190 kilogram times 9.81 meters per second squared. And when you punch your calculator very well, you will get W to be equal to 1,863.9 Newton. Now, the second part of the question asks us to determine the weight of the rover on the surface of Mars. Now, on the surface of Mars, the gravity has been given us to be 3.68. So when you multiply that by the mass of the rover, you get 190 times 3.68. And then when you punch your calculator very well, you will get the weight of the rover on Mars to be 699.2 Newton. Now the third part of the question is asking us to calculate the weight of the rover at a point 3,622 kilometers from the center of Mars. The spacecraft reached at atmospheric entry interface point at this particular value. So when you compare that 3,622 to the radius of Mars, you will see that that point lies outside the surface of Mars. So you, in this case, to calculate the weight of the rover, you have to use the gravity at that height and multiply it with the mass of the rover before you can get your answer. And so when you do that, you realize that from the center of Mars here, this is our mass, and then from the center of Mars to the surface is the R, and then from the surface to the point, we donate it by h. Now R plus h is given to us to be 3,622 kilometers. And so when you do that, you see that you get this expression, and then you know the radius of Mars to be 3,490. When you subtract from the 3,622 kilometers, you get your h to be equal to 3,622 minus 3,490, and that, when you punch your calculator very well, you get 132 kilometers, and that gives us the height above Mars surface. And now we have to calculate the gravity at that height. Gravity at a height equals to 132 kilometers above Mars surface. And then when you do that, you know your gravity at a height above Mars surface to be equal to gravity on Mars times the radius of Mars squared all over the radius of Mars plus the elevation, 132 elevation, all squared. You know your gravity on Mars to be 3.68, and then you know the radius of the Mars also to be 3,490 times 10 exponent 3 meters, and then you know Rm plus h, the radius of the Mars plus that height, given to be 3,622 times 10 exponent 3 meters. And so you carefully slot in these values into this formula, and then you get this expression 3.68 times 3,490 times 10 exponent 3 all squared all over 3,622 times 10 exponent 3 all squared. And when you punch your calculator very well, you will get 3.4167 meters per second squared to be the gravity at that height. Or if you don't want to use this expression and put it in, you can separately slot in the values of the radius of the Mars, which is 3,490 times 10 exponent 3 meters, and then the height, which we have determined to be 132 times 10 exponent 3 meters. And then when you slot in that value, you realize that you also arrive at the same figure with previously gotten 3.4167 meters per second squared to be the gravity at the elevation we are to find the rover's weight. Now the rover's weight at that height will be equal to the mass of the rover times the gravity at that height or elevation. We know the mass of the rover to be 190 kilogram, and then when you slot in those values into W, which is W equals to mrgh, you will get 190 times 10 times 3.416 7 meters per second squared, and when you punch your calculator well, you will get the weight of the rover at a point 132 kilometers away from the center of mass to be 649.173 Newton.